Welcome everyone to the AI Research Bites. This series, as always, is short and informative talks showcasing cutting-edge research work from ServiceNow AI Research and other AI practitioners in ServiceNow. The AI Research Bites are open to everybody, especially those interested in keeping up with the fast-paced AI research community. So today's session features a 15-minute talk from Ahmed Masry on the latest advancements of AlignVLM, and will be followed by a 10-minute Q&A. So Ahmed is a PhD student in computer science at York University in Toronto and a visiting researcher at ServiceNow Research. His research focuses on developing multimodal vision language models and benchmarks for chart, table, and document comprehension. His work has been published in top-tier conferences like ACL and EMNLP, accumulating over 1,199 citations on Google Scholar. He is also an active open source contributor, providing models and datasets with tens of thousands of downloads on Hugging Face. So thank you, Ahmed, and up to you now.
Thank you. Thank you so much. So hi, everyone. So today I will be presenting AlignVLM, which is about bridging vision and language latent spaces for multimodal document understanding. So for your information, this is just a short disclaimer that the upcoming statements are to the best of our knowledge. So our agenda for today, first, I'm going to walk you through the motivation and some background, and then I will walk you through our solution, the Align connector, followed by the experimental setup, the results, and finally the key takeaways. So let's start. So the first question we ask is, why does this topic matter? Why multimodal vision and language models? So in enterprise applications or setup, you will often encounter text-rich visuals, such as like charts, infographics, PDFs, or tables. And in order to analyze these visuals or extract data from them, you need an AI model which can understand both the visuals and the language. So how do these vision language models work? So over here, you can see the architecture of a vision language model, a simple architecture. So the architecture has three main components. The first component is a vision encoder, which was pre-trained to understand images. The other component is a large language model, which was pre-trained to understand text. And finally, you have this connector component over here, which basically maps the vision feature from the vision encoder to the LLM input space. So you can think of this connector as a translator. It translates visual features into textual features. So there has been a lot of work on the vision encoder side and the LLM side, but there has been very little work on the connector itself. So the key question we ask in this project is, how can we design a good connector to effectively align the visual features with the LLM input space? So before we answer that question, let's have a look at this example over here. So imagine you have that image and you encoded it, and right now you have some visual features in the vision space. So, and on the other side, you have the text space of the LLM. So over here, you can see, let's say, the points representing the LLM tokens or words, basically words which the LLM can effectively understand. So what you want to do with your connector is you want to map the vision features from the vision space into the text space while preserving the semantics. So for example, if you have some vision features coming from an image of a tree in the vision space, you want to map them to the text space so that they can land as close as possible to the word, let's say, tree. So ideally, what you
is
existing connectors out there, when they do this mapping, they don't enforce any hard constraint on this mapping process. And this can become problematic when you have some noisy inputs, because if you have some noisy inputs in the vision space, and you map them, they can land anywhere. But ideally, you want to keep them as close as possible to this region. So how can we design a connector to do that? We present the Align connector. So over here, you can see the architecture of our Align connector and the AlignVLM model. So basically, we have two kinds of inputs, a text input. So for the text input, it gets processed as normal. First, the text gets tokenized, and then the relevant LLM text embeddings are selected, and then they are given to the LLM as text inputs. For the vision inputs, it's a little bit different. So first, we encode the vision features, and then we convert the vision features into some probability distribution or probabilistic weights over the LLM text embeddings. So basically, we convert the image into probability weights, which we use them to combine the text embeddings together using a weighted average sum operation. So mathematically, this operation over here will force all the vision features to be in the convex hull of the LLM text embeddings. And these will become the vision inputs to our model. Another way to look at it is that the vision inputs and the text inputs, they are coming from the same source in this model design, right? So they are coming from the LLM text embedding matrix in both sides. The image, we only use the image to produce weights or probabilities, which we just use to combine those LLM text embeddings over here. So now I'm going to walk you through our experimental setup and how we trained and evaluated our models. So we train our model in 3 stages. The first stage is natural image understanding. The second stage is document understanding, where we train the model on our big docs data set. And finally, in the third stage, we train the model on our big docs dog downstream data set, which enables the model to follow the user queries and prompts and questions. And for the different model components, for the LLM side, we use the Llama 3.2 family of 1 billion, 3 billion, and 8 billion parameter models. So we experiment with 3 different model sizes. For the vision encoder, we use the Siglip 400 million model. And for evaluation, we evaluate our model on 9 diverse benchmarks spanning documents, infographics, charts, tables. All right, let's talk about the exciting part, which are the results. So for the results, we want to answer 2 questions. How effective is the Align connector? And how effective is the AlignVLM model, the whole model together? So in order to do that, we have conducted 2 key comparisons. The first one, we compare the Align connector against the previous connectors out there. So we designed an experimental setup where we controlled the setup, like we use the same LLM, we use the same vision encoder, same training data. So we train the models on the different models under same configurations, while we only changed the connector. So the main purpose is we want to isolate the true impact of the connector itself on the performance while keeping all the other variables in the experiment as fixed as possible. The other key comparison is we compare our AlignVLM model, the model we trained with the Align connector, against the other vision language models out there. And we have 3 categories of models to answer different questions. For example, we want to tell you first, we want to convince you why should you choose AlignVLM if you already have data for fine-tuning. And when should you choose AlignVLM if you don't have data for fine-tuning? And when AlignVLM is a better choice over black box models. So let's answer all these questions in the upcoming slides. So first, in this slide, you can see we compare the Align connector against the previous connectors out there, such as OVIS, MLP, Perceiver, Resampler. And in this figure, you can notice that we have 9 different diverse benchmarks. And it's pretty obvious that the Align connector, the orange circle, is actually outperforming all of them in all the benchmarks. In fact, on some benchmarks, the accuracy is way much higher, so such as the W2Q benchmark. So this proves that our Align connector is much better alternative than the previous ones. Now let's compare our AlignVLM model against open source base VLMs. By base VLMs, we mean that we took some base VLMs out there and we trained them on the same data sets as our models using the similar configuration setup. So we do this to ensure a fair comparison. And over here, you can see the different results. So we have 2 categories of models. The small model category of 1 to 3 billion parameter models, and the larger model categories of 8 billion to 11 billion parameter models. And it's pretty obvious that on both model categories, our AlignVLM models are actually outperforming the other ones. For example, our AlignVLM 8 billion is outperforming Llama 3.2. And over here, you can see AlignVLM 3 billion, and even the 1 billion is outperforming 0.2 VL. Now let's compare our AlignVLM model against the open source Instruct vision language models. So by Instruct vision language models, we are referring to models which were just trained on undisclosed datasets by their vendors, and we don't perform any additional fine-tuning on these models. So the comparison over here may not be entirely fair because models were trained on different data sets. But hey, let's put our model to the test and see how well it performs against those open source ones. So on the small model category, you can notice that AlignVLM 3 billion is actually outperforming very famous models such as Qwen2VL 2 billion, InternVL 2.5, and so on. On the larger model category, you can, even though AlignVLM 8 billion doesn't have the highest performance, it's performing very competitively with open source models. Finally, let's compare AlignVLM against closed source VLMs. So closed source VLMs are basically trained on undisclosed datasets. We have very little knowledge about their architecture or training details. So these are models such as GPT-4, Gemini, and Claude. So as you can notice over here in this in the results, you can notice that our AlignVLM model of 8 billion, it's outperforming Gemini Pro 1.5, Claude, Sonnet. However, it's slightly lower than the GPT-4 model. So AlignVLM is performing very competitively against those closed source models. In addition to the previous results, we have also conducted an interesting experiment to validate our hypothesis that Align connector is more robust to noise. So recall these images from the previous slides. Basically, here you have the vision space and some visual features, and over here you have the text space with the LLM text embeddings. And remember, we were mentioning that for ideally you want all your visual features to be mapped to this region over here in the text space. However, imagine if you have some noisy inputs. I mean, your connector can map them anywhere. But we argued that the Align connector will force all the vision features to land in this region over here, which is the convex hull. So let's see how well is this hypothesis, or how true is it? So we conducted an experiment where we add some random noise to the inputs to our connector. And then we basically measure the performance before adding the noise and after adding the noise. And we compare two connectors, our Align connector and the MLP connector, which is the most widely used connector out there. And as you can notice, for our connector, we only noticed a 1.6 drop in performance. However, for the MLP connector, we noticed a massive 25% drop in performance. So these results over here validate our hypothesis that the Align connector is much more robust to noise. So to summarize, in this talk, basically multimodal document understanding are critical for AI agents that can handle complex data, such as like charts, tables, PDFs. And the Align connector enhances the vision language models for document understanding tasks. And as you have noticed from our results, the AlignVLM is a state-of-the-art and efficient model for document understanding. For the upcoming weeks, we plan to open source the model and the code base. And also we are working on improving other architecture components in VLMs. So if you are interested to read more or learn more about this work, feel free to check out our paper on arXiv. And yeah, that's pretty much it. Thank you so much for listening.